So, thank you very much for attending. My name is Massimiliano, and I'm part of a CITES group at EPFL. So, just a very brief introduction. As a group, we manage the HPC clusters that EPFL provides to the scientific community, and in particular, I am responsible for the automated deployment of scientific software on our clusters. And that brings me to the topic of today, introducing a relatively novel tool to install scientific software on supercomputers, Spack. So, scientific software is complex to build. And this complexity mainly arises because of one thing, because of people in HPC are really willing to trade up anything for performance. And this is really sensible, but it also causes what is known as the combinatorial explosion of software. So if you think when you log into an HPC cluster, you won't have available just one compiler. You will have many. You will have many different versions of the same library, many different flavors of the same application, many MPIs, possibly many LAPACs. And all of that is mostly because each particular combination of those things will be the best pick in terms of performance for one particular problem or one particular set of users. And there is one thing, though, that traditional tools are not handling this complexity well. And what people ends up doing then on HPC clusters is installing scientific software manually or coming up with, let's say, an homebrewed scripting system. And of course, this is not scalable, and in the long run, it can threaten the productivity of both scientists and cluster maintainers like me. So, wouldn't it be better if even scientific software was easy to deploy and easy to use? And if we had software that was easy to deploy, well, the benefit would be evident. Like, software developers could move to the next supercomputer and set up their environment to start working on their code. So they will be more focused on their actual work than on building the environment that they need to start working. Users will be more confident that the applications that they are using on the cluster and that we installed are the mostly tuned for the machine at hand and the problem they want to solve. And that's because we could explore more the deployment space and select whatever is the best sample we found. So it is evident that to reach this, we need more automation. And the question then becomes, how do we automate things then? And the answer I would like to give you today is using a package manager, using Spack. So Spack is an open source project originally developed at Lawrence Livermore and hosted on GitHub. When I say open source, I don't just mean that you can download it and that's it. I mean that you can really interact with the community. So the guys at Lawrence Livermore are really open to accept any kind of contribution in terms of packages, in terms of core functionalities, or even just in terms of discussion where the development should be going. And in fact, I am one of the major external contributors, and I started just because I started using the tool, and I started chatting with them, and then pushing modifications. So the slide here is just meant to show that whenever we develop, we really strive to maintain things simple. So to get the tool, you just have to clone a Git repository To set it up, you have to source a shell script, and then an intuitive command, I think, like Spack install HDF5, will download, extract, configure, build, and install HDF5 along with its dependencies. And just to reiterate on the concept, Spack is a package manager. And this means that what it does is leverage whatever build system is in place to build a package and coordinate this build with that of its dependencies. So stated otherwise, it is by no means a substitute for lower level build systems like AutoTools, like CMake. Instead, it uses what is in place, and it embraces the principle of pristine sources. This means that if you want to package your software with Spack, of course, you don't need to modify your source code. All you need to do is just to write a small Python script, and we'll see it later, in which you describe how you should build your software and what are your dependencies. And in this sense, it acts like a big cache of recipes. And the effort is really shared among people coming from different centers in the world. So package managers have been around for 30 years. And somebody may ask, and I think he will be right, what makes Spack different from other tools? Well, first and foremost, it was designed from the ground up to deal with the combinatorial complexity that we've talked about before. So when you ask Spack to install something, say MPI-Lex, what happens in the internal is that you have a full-blown graph representation of the package and all of its dependencies. And whatever property takes part in making this graph unique, it also participates into an hashing function, so that we can create a one-to-one mapping between an hash and the actual installation that you want to perform. And this solves the first problem you will encounter when designing a package manager like this: how you should lay out the root installation prefix. Well, we use the hash to identify the particular graph from which the installation stemmed. And one other important thing is that we decided to use rpath at linking time. And this means, basically, I don't think I have time to go into the details, but this means basically that things at runtime work the way they were built, and they cannot be overridden by LD library path or other changes in the environment. So, being a package manager, Spack doesn't only install things, it also keeps track of what it has installed. And you can query whatever you want later on. So in this case, Spack find call path will tell you that you installed 2 versions of call path, one compiled with CLang and one compiled with GCC. And you can bring this query to the level of detail you want. Here, for instance, I show a case where I want the full-blown graph of dependencies along with a short version of the hash for each package. Okay, another very, very nice feature is that Spack comes also with a domain-specific language to express in a very neat way every detail you want for the installation that you are going to perform. Take this first line, for instance. When you say Spack install MPI-Lex, you are implicitly saying, I just want a version of MPI-Lex working. I don't care about the details. Please, Spack, fill it in the blanks for me. But you can be more specific. You can say, I want MPI-Lex at version 3.3. you can say I want MPI-LX at version 3.3 compiled with GCC at version 5.3.0. You can activate the so-called variants, meaning flags that will act in some way, depending on the package, performing different configurations for your package. In this case, most likely activating the thread support. You can inject compiler flags. Here you're saying that when you compile C++ code, C++ source files, you always want -03 to be there. You can compile for different targets, and with the caret, the syntax becomes recursive. So you can specify the same things for your dependency. The last line reads, I want to install MPI-LX at version 3.3, which depends on MPI-CH at version 3.2, compiled with GCC at version 5.3. So this syntax gives you full control over the combinatorial build space, but also lets you specify only the details that you care about. Then, Spack can constrain versions and options of dependencies. So let's go with the usual example. Here you see, for instance, that asking for libelf at this version, I get this dependency through two paths. It's a direct dependency of dyninst and a direct dependency of libdwarf. By construction, Spack ensures that within its graph, a single package is present only once. This means that it ensures API consistency. There will be no way that you get two different versions of libelf because libdwarf was compiled linking against one and dyninst against another. And not only Spack can do this with concrete packages, but it can also do the same thing for virtual packages, packages that just express the dependency against an API, where different API-incompatible versions exist. So if you say that MPI-LX depends on MPI, Spack will ensure that you have just one implementation in this graph when it comes to installing, and the graph will be, let's say, fully specified. So how do we go then from what you specify in the command line to what is really installed? Well, the process is really a two-step process. The first step is called normalization. And during normalization, we basically add all the unconditional dependencies to your graph. If you take into account this example, we add all the dependency we know of without further details, and a dependency on an API. Then the next step kicks in, which is called concretization. And in this step, Spack uses a certain logic to fill in the blanks, to decide what to put for all the details that you didn't specify. And, well, for those of you that, let's say, would like to know this, this is basically solving a set problem. But it works, and it gives you the full-blown specification of what you are going to install. That, I mean, in Spack jargon, we call this abstract specification and this one concrete configuration. Okay, this is a bit more complex, but should explain graphically what goes on once you have your concrete configuration when it comes to build packages. Basically, from your graph, from your concrete graph, Spack starts to explore it from the bottom up, and for each package that has not been installed yet, it forks a new process, and it sets up the environment for the build, and in this case, the colors for the boxes are not like random. The blue one means that the framework is in charge. When it comes to red, it's the package that implements callbacks to influence what's going on. So it sets up the environment to build this particular package, and it goes through the installation process, which for an AutoTools package could be just the configure, make, and make install. Each one of these stages won't call directly the compiler, but will call a compiler wrapper that will add search path for headers and libraries, will add flags to add our path, and on Cray, it will ensure to load Cray modules. And it also injects compiler flags on demand if you specify them from the command line. So with that approach, we can maintain different builds in terms of environment isolated from each other. Okay, just a glimpse on how a package looks like. As I said, it's just a small Python script. You usually start with some metadata, like a description for the package and URL where to get the tarball, the home page. You specify the version with an MD5 sum that is expected. Here, I don't show, you can specify like variants. If you have patches, sometimes they are necessary. You can also specify how to patch your code. And of course, the patch itself will be stored with a recipe. You describe your dependencies, and as you can see, you can also constrain them. So the second line says that Dynins depends on Boost. That must be at least version 132. And well, I wouldn't dwell much on that, but one thing that I didn't mention is that edges in the graph are colored. And the colors are basically, it's no other combination of build, link, and run. And then you have just the recipe that describes how to build your package once your dependencies are in place. And as you can see, we also provide wrappers to common, let's say, calls, so that for packages, the experience would be more or less the same as building a thing manually. And finally, Spack does not only aim at installing software, it also wants to integrate with whatever workflow is currently used, either on clusters or on workstations. So for cluster, this means that it's also able to generate module files, either non-hierarchical Tcl module files or Lua hierarchical module files that needs to be used with L mode, of course. And the module file generation, both in terms of layout and content, can be customized to a fair extent. So don't be scared by those names, because those are just the default. You can specify really the directory layout. You can specify whatever you want as content in your module file, just writing a simple YAML configuration file. And if anybody is interested in knowing more, just catch up with me later. And I think, how much time do I have left? So, okay. So I'll go fast over this because, well, the scope is supercomputing, but I just want to let you know that if you work on your local workstation, you can even create a view like, let's say, a sort of virtual environment with just a few of the applications that you installed in some part of your path. So, let's go back to being social. How can you contribute? Well, as I said, the code is hosted on GitHub, and the guys at Livermore really built up a very big and very nice community. And here you see just the major contributor. Actually, I think there are more than 30 organizations using the tool and more than 100 individual contributors. So Spack is already used in production, at least in those 3 sites, but I think there are more. And well, for development, we use Git flow-like development. So, you know, you fork, you have something smart in mind, you code it, and then you issue a pull request, and people start discussing over what you have done, how to improve it, and eventually the thing will get merged. So this is just to show you that the development really went beyond just Livermore. Of course, it started there. Those are the line of code. This is time, and I think it stops like at February this year. Up, you see the line of code in packages, down in the core framework. So what you see here is that the first contributor is not Lawrence Livermore anymore. It's Argonne, because we had like a tremendous guy that packaged, let's say, the Word. Here you see when he packaged like the whole X system, this big spike. And well, Livermore is second, then it's a EPFL, then University of Iowa, and even in terms of the core framework, the blue one is Lawrence Livermore, the green one is us, then it's Argonne, and so on. So you see that contributions are really accepted. And finally, Spack is well documented. So we strive to keep documentations up to date and in syncs. And well, for that, we use Sphinx and read the docs. So I think I'm basically done. And if there are a few questions, I would be more than happy to take them.